Good morning. This is Engineering Statics. So, sixth lecture. Once again, this is the fifth edition of the Hibbeler text. So, in our previous lecture, we left off with working some problems and determining the magnitude of moments, where we define moment or moment force as a vector quantity that describes the tendency for a body to rotate about a point when that body is subjected to a force. So moment being a vector is completely described with magnitude and direction. The magnitude of the moment about a point, and we said typically we'll call the point O as in the origin. So capital M subscript O is the applied force that's causing the rotation times D, which is our moment arm. Which is the perpendicular distance from the point, in our case, O, to the line of action of the force F. So to get us back refreshed on that concept, let's work a few problems in the text dealing with the magnitude, and then we'll start working to the vector analysis of the moment. So let's start with problem 3-5. This is on page 96 in the text. It says, determine the moment about point B of each of the three forces acting on the beam. So in this case, we have a point B. Okay, so we have a F1. This is 375 pounds force. We have an F2. This is 500 pounds force. Our point B is here. And we have an F3. This 160 pounds force. The distance here is 8 feet. Distance here is 6 feet. And the distance between F2 and B, this is 5 feet. The angle between F3 here is 30 degrees. And the thickness of this beam is 0.5 feet. I believe that's all the angle here for F2, this is a 3-4-5 triangle. I believe that's all we need. So they want us to determine the moment about point B. Remember, the tendency to rotate caused by the force about point B. And remember, we need the magnitude of the force and the perpendicular distance of the line of action of the force about point B. So starting with F1, remember we said now sense of direction, counterclockwise equal positive, clockwise rotation equals negative. So the force tends to cause a clockwise rotation about the point in interest. The value of the moment is negative. If the force tends to create a counterclockwise rotation about the point, then the magnitude of the moment is a positive value. So my moment caused by F1 about point B, counterclockwise being positive, equals. So this is my line of action of force F1, and it's perfectly vertical. What is the perpendicular distance from between F1 and B? Well, that is, let's write it out. So remember we said magnitude of the moment is force times perpendicular distance. So there's 375 pounds force, which is the value of F1. The perpendicular distance being 6 feet plus 5 feet. Multiply this out, you get 4,125 pound force feet. And the F1 about point B is to the left of point B and is pushing down, so that's causing counterclockwise rotation, so positive. Let's look at F2. The moment caused by F2 about point B. Now F2 is at an angle and is given, the angle is given to you 3, 4, 5 similar small triangle or slope triangle. So it's two components of this force. If you look at it that way, F2 has a component that's vertical and horizontal. Now the horizontal quantity of F2 here, as you can see, its line of action runs through point B. So therefore, it will not cause a moment about point B. There has to be a perpendicular distance between the line of action of the force and the point of which you're trying to cause a rotation about. So we can eliminate the horizontal component. The vertical component, this line of action, there is a perpendicular distance between that and point B. So let's write it out. 500 pound force, that's the magnitude of F2. But we want the vertical component, so that's the 4/5 leg of the slope triangle, 4/5 ratio. It's the vertical component. So now we have the vertical component of F2. Well, what is our perpendicular distance between F2 and B? That is 5 feet. Multiplying this out, you get 2,000 pound force feet. Now, once again, this F2 is to the left of point B and is pulling down. So this is causing a counterclockwise rotation, which is a positive. Last but not least, F3, the moment caused by force F3 about point B. So F3, once again, this is at an angle. So we have both a vertical and horizontal component of F3. So the F3, if you look at this as a right triangle, then the horizontal component of F3 would be sine the B leg, since this is our angle theta. And the vertical component would be cosine, the A leg. So cosine of 30 will be our vertical component. Sine of 30, the B leg, will be our vertical component. The magnitude of F3 is 160 pounds force. So we have 160 pounds force times the sine of 30 degrees. Once again, that gives us the horizontal leg. Now, what is our perpendicular distance between the horizontal leg B and, the horizontal leg sine of 30 and point B? That would be this component of F3 and B. Well, that's the thickness of the beam, 0.5 feet. And the vertical component, this leg, goes through point B, so it does not cause a rotation. So there's no moment caused by that. Only the horizontal component causes a rotation about point B. Solving that out, 160 pounds force times sine 30 times 0.5 feet, you get 40 pound force feet. Let's take a look at another problem. Problem 3.7, same page, 96 in the text. Here they want to determine the moment of each of the three forces about point A. Point A being up here. Here for F1, 250 newtons at an angle this is 30 degrees. We have an F2. This is 300 newtons. This is an angle of 60 degrees. We have an F3. This is 500 newtons. And it gave you the slope triangle. This is 3, 4, 5 triangle. The distance here is 4 meters. The distance here is 3 meters. The distance here is 2 meters. I believe that's everything the problem gave us. So they want us to determine the moment of each of these three forces about point A. So remember, for the magnitude of the moment, it's just the magnitude of the force times the perpendicular distance from the line of action of that force to the point A. So if we start with F1, so counterclockwise being positive, moment of F1 about point A. The moment that force F1 causes about point A, that's how we say that. This is equal to the magnitude. So we have F1 is actually at a angle. So let's do a different color. Clear. So there is a horizontal and vertical component to F1. The horizontal component, the line of action of that component goes through point A, so that it causes no rotation. The vertical component, there is a perpendicular distance between that and point A, so it causes a rotation. So let's take the vertical component, which in this case would be the A leg. So it's cosine of 30. So that would be F1, which is 250 newtons, times the vertical component of that angle, which is cosine of 30. Let's take some space, a little bit more space. (250 newtons) times the vertical component, which is the A leg, cosine of 30 degrees. So that gives us the vertical component of the force, F1. And the perpendicular distance is 2 meters. Solve this out. And with F1 pushing down to the right of point A, it's causing a rotation in the clockwise. So that'll be negative value. Clockwise being negative, counterclockwise being positive. So this comes out to be Newton meters, force times distance. Now, F2 once again, there's a vertical and horizontal component of F2. The horizontal component, the line of action of that goes through point A, so once again it causes no rotation. The vertical component, there is a perpendicular distance between the vertical component of F2 and point A. So the vertical, this is our angle theta, that's the B leg, so we're talking sine. So it'll be 300 newtons times sine of 60 degrees times the perpendicular distance, which is 3 meters plus 2 meters, which is 5 meters. That's the perpendicular distance between F2 and A. And once again, with F2 pushing downward and to the right of point A, it's causing a clockwise rotation, which means it's negative. Multiplying this out, this comes to be about 1299 Newton meters. Last but not least, the moment caused by F3 about point A. So F3, once again, has a vertical and a horizontal component given to you. The angle there is given to you by a slope 3-4-5 slope triangle. So the horizontal component, which is the 3/5 ratio, this is the line of action of that. There is a perpendicular distance between the horizontal and A. The vertical component, given to you this line of action, there is a perpendicular distance. So we have to take both components of F3 into consideration as they cause a moment about point A. So the horizontal being the 3/5, let's take that first. So 500 newtons times 3/5 gives us the horizontal component. The perpendicular distance there is given to us as 4 meters. Now, the horizontal component being below point A and pulling to the right is causing a counterclockwise, so positive rotation about point A. So that's positive. The vertical component is pulling downward from point A, so that's causing a negative rotation about point A because it's clockwise, pulling down about point A. It'll be 500 newtons. And the vertical component is the 4/5 leg. And the perpendicular distance being the 3 meters plus the 2 meters being 5 meters. Solving this out, you get 1,200 Newton meters minus 2,000 Newton meters gives you a negative 800 Newton meters. Let's take a look at another problem. Take a look at problem 3.9. Same page. 3.9, determine the moment of each force about the boat. So they give you FB is 40 pounds force, and FC is 50 pounds force. So we want to know the moment that each force causes about point A. So let's say, let's see. Degrees between FB and the perpendicular to the bar, and we have let's see, this is 30 degrees, this is FC, this is FB, 30 degrees there. This distance here is 0.75 feet. This is point A, and this distance here, 2.5 feet. And they gave us FB and FC. I believe that's everything. All right. So this is obviously point B, this is obviously point C. Okay. So once again, the magnitude of the moment is the force times the perpendicular distance. So it's about point A, counterclockwise being positive. Magnitude of moment of, say, force B, about point A. So the perpendicular distances, we have to figure those out. So the FB is at an angle of 25 degrees, different color. So it has a vertical component and a horizontal component. If we take the horizontal component here, it is on the line of action of the force B, then goes through point A, which means it causes no rotation. We take the vertical component, then that there now has a perpendicular distance between the line of action of force B and point A. The vertical component would be, if this is our right triangle, the A leg, so cosine of 25. FB was given as 40 pounds force. A leg cosine of 25 degrees gives us the vertical component. The moment then is the perpendicular distance between the line of action of that force and the point A. Well, that's 2.5 feet. Multiply this out, you get, and FB is pushing up, and it's to the right of point A, so it's causing it counterclockwise, so positive. So that's 90.6 pound force feet, and it's counterclockwise, so it's positive. The moment of FC, the FC causes about point A. Once again, FC is at an angle. If we take the horizontal component of FC, it goes through point A. Therefore, the line of action, there is no perpendicular distance between the line of action of the horizontal component of FC and point A. If we take the vertical component, then there is a perpendicular distance between the line of action of the vertical component of FC and point A. So we can work with the vertical component. If this is our angle theta, vertical component will be leg A, cosine of 30. So FC was given as 50 pounds force times cosine of 30. then times the perpendicular distance, which is 2.5 feet plus 0.75 feet. Multiply that out, and you get 141 pound force feet. FC is to the right of point A and pushes up, so it causes counterclockwise, so a positive value. Let's do one more problem, and then we'll get to some vector analysis moments. Let's look at problem 315. This is page 97. Let's draw a figure real quick. So 2 men exert forces of F equals 80 pounds force, and P equals 50 pounds force on the ropes. Determine the moment of each force about point A, and which way will the pole rotate, clockwise or counterclockwise. So they gave you this distance here. This is 12 feet. And they gave the distance here. This is 6 feet. So the moment, we'll say counterclockwise or positive, the moment that force F, and I'm sorry, point A is down here, force F causes about point A, force times perpendicular distance. The vertical component of force F goes through point A, so no perpendicular distance between the line of action of the vertical component of point F. But the horizontal component, there is a perpendicular distance between that line of action. So then that'll be our 80 pounds force times the horizontal component, which is the 4/5 ratio of that. The perpendicular distance then being 12 feet. Multiply this out, you get 768 pound force feet. Now that is pulling to the right of point A, so it's causing a clockwise or negative. So we'll say clockwise here, but basically a negative rotation about point A, because counterclockwise direction is positive. Now, the moment caused from force P about point A, force P magnitude being 50 pounds force. Then they gave you the angle here. Once again, the vertical component of force P goes through point A, so there's no perpendicular distance between the line of action of the vertical component of the force in point A, but the horizontal component of point P, there is a perpendicular distance. So working with the horizontal component, that would be cosine of 45 degrees, because that's the A leg component we're talking about. So cosine that angle times the perpendicular distance, which is 6 feet, plus 12 feet. This comes to 636 pounds force feet. Now this is pulling to the left of point A, causing a counterclockwise, so positive. So the question asks, which way would the pole rotate? Well, since our negative or our clockwise rotation is greater than our 768 clockwise rotation is greater than our 636 counterclockwise rotation, then it will rotate or tend to rotate clockwise. So let's take a break from solving some magnitude problems and get back to work in the vector analysis of moments. So we will work our moment of a force using Cartesian notation. Remember, vectors need magnitude plus direction, and Cartesian vector notation makes that exponentially easier to write and work with. So we've introduced a technique from vector algebra called cross product. We're just going to introduce it as a technique. We're not going to dive too deep into it. But essentially, it means the cross product is given by this symbol x. This does not mean multiplication. It means cross product. This vector cross that vector. So we have two vectors, A and B. The cross product of A and B gives a new vector, C. So C is equal to vector C is equal to vector A cross vector B. That's how you say and write that. It does not mean multiply. I'll write that one more time. Does not mean multiplication. This is read as vector C equals vector A cross vector B. And then the magnitude of this new vector C is the magnitude of vector A times the magnitude of vector B times the sine of the angle theta between their tails. And I'm on page 83 in the text, section 3.2. So you can follow along. So let's go over some laws of operation of cross products. The commutative law does not apply. And that vector A cross vector B does not equal vector B cross vector A. Instead, vector A cross vector B is equal to minus vector B cross vector A. Another law we'll call associative law. if the cross product is multiplied by a scalar, then the law of associative law does apply. So if you have vector A cross vector B, and you multiply by some scalar value, scalar quantity, I should say, lowercase a, this is equal to scalar value A times vector A cross vector B, which is also equal to vector A cross scalar value A times vector B. And this is also equal to vector A cross vector B times scalar value A. And the distributive law applies as well. Most of the problems, we're not going to dig this deep into it. This is more just introducing you to these laws and terminology. From a pure vector algebra perspective, we're not going to be diving too deep within the scope of this course, but it's helpful to become familiar with these laws and how to work them. So the distributive law, if we have vector A cross vectors B plus vector D, then this is equal to vector A cross vector B plus vector A cross vector D. So going back to our cross product, we said vector C equals vector A cross vector B. And we said the magnitude of vector C is the magnitude of vector A times the magnitude of vector B times the sine of the angle theta between their tails. Now, vector C has a direction that's perpendicular to the plane containing A and P. So if we have a vector A here, and this tail is joined to vector B, and they are in the same plane, theta is the angle between their tails, then vector C is perpendicular to that plane. Therefore, we can write vector C equals vector A cross vector B as A, B sine theta times unit vector U sub C, because here, remember, vectors are defined as magnitude and direction. The magnitude of vector C, we said, is AB sine theta. Well, that's here, that's here. Direction then is given by the unit vector U sub C, which is in the direction of vector C. So say that one more time, work through it. Vector C is vector A cross vector B. The magnitude of vector C is the magnitude of A times the magnitude of B times sine of theta, which is the angle between their tails, right here. Well, if vectors are magnitude and direction, and we define a unit vector U sub C in the same direction as as vector C, then we can rewrite vector C equal vector A cross vector B, which is the magnitude of C times the direction of C. So the magnitude of vector C is AB sine theta, and direction C is unit vector U sub C. Now, and we talked about three-dimensional space and our coordinate direction angles in the previous lecture in chapter 2. And we were working in three-dimensional space with our three axes, X, Y, Z. And we had our associated unit vectors, unit vector I on the x-axis, J, y-axis, and K, z-axis, respectively. Well, each one of these axes are perpendicular to each other, 90 degrees apart, perpendicular, right? Let's see, all three axes. And this being Z, Y, X, perpendicular, perpendicular, and perpendicular, which means 90 degrees apart. So then the cross product, we said again, vector C is vector A cross vector B. Vector C is AB sine of theta. I'm sorry, the magnitude of C. AB sine of theta. Well, for then our IJK unit vectors with all their with the X, Y, and Z axes all 90 degrees apart, sine of 90 degrees, and theta being where their tails join. So this will be our unit vector J, unit vector I, unit vector K, where the no tails are all 90 degrees apart. So then sine of 90 degrees is 1. So when doing our Cartesian unit vectors cross products, where we say eventually I cross J, or J cross K, etc., the magnitude of it will be IJ sine 90 degrees. And the magnitude of these unit vectors are 1, so that's equal to 1 times 1 times 1. So here's a shorthand rule of determining direction when doing cross products of Cartesian unit vectors. So I'll draw the circle. Let's see. Boom, boom, boom. I, yeah, J, K. Positive is counterclockwise. Clockwise is negative. And it goes in this order. So I cross J equals K. J cross K equals I. K cross I equals J. Likewise, I cross K equals minus J, negative J I should say. J cross I equals negative K. And then K cross J equals negative I. and I cross I equals 0. J cross J equals 0. K cross K equals 0. So you can memorize these or simply use the, I'll rewrite this circle so it'll be easier to view. Counterclockwise being positive, clockwise being negative. So if you go on this way, I cross J gives you K, J cross K gives you I, K cross I gives you J. But if you're going this way, J cross I gives you negative K, I cross K gives you negative J, K cross J gives you negative I. So why do we care, right? Well, let's take a look. So if we have two vectors, vector A, and we'll define that as remember magnitude and direction, AXI plus AYJ plus AZK. Magnitude of A in the X direction times unit vector I, magnitude of A in the Y direction times unit vector J, magnitude of A in the Z direction times unit vector K. Magnitude and direction. This is in Cartesian notation. And we have vector B, likewise, BYJ plus BZK, magnitude and direction. And if we said vector A cross vector B, we have to multiply each one out. So A cross B, it's going to be a little lengthy, but let's get through it. Be AX times BX. Then I cross I. Then AX times BY. I'm taking this, multiplying everything in here. Then I'll take this, multiplying everything in here. Then I'm going to take this, multiplying everything in here. So it's AX times BY, I cross J, plus AX times BZ times I cross K. Then AY is next, plus AY times BX. Then it's J cross I plus AY times BY. Then it's J cross J plus AY times BZ. Then it's J cross K plus AZ times BX. Then it's K cross I plus AZ times BY. K cross J. And lastly, AZ times BZ. K cross K. Well, from the previous page, where we know I cross I is 0, J cross J is 0, K cross K is 0, or I cross k is negative j, and likewise and so forth, we can simplify this expression. So rewriting this now, or simplifying, I should say, a cross b. So once again, any unit vector cross itself is 0. So we have an I cross I here. This gives a 0. We have a j cross j here. This gives a 0. This whole thing is 0. This whole thing is 0. We have a k cross k. Whole term is 0. Furthermore, with I cross j is k, j cross k is I, k cross I is j, we can simplify these further. I cross j gives us k. I cross k gives us negative j. J cross I gives us negative k. J cross k gives us I. K cross I gives us j. K cross j, negative I. So now we can simplify this further to AY times BZ. We'll combine all our i's first and then our j's and our k's. So it's AY BZ times I. Or I should say, I'm sorry. AY times BZ, I, and then we have an I down here, plus I should say minus, because this is negative I right here, minus AZ BY unit vector I. So take care of this and this terms. Then we have minus AX BZ, finding our J's now, minus AZ BX unit vector J, plus find our K's, AXBY and the last minus AY BX K. So this is a long way of doing it. We won't do it this way in the class, just to showing you that. We will actually do it the matrix method. Of determinants. So you saw the lengthy way of doing vector A cross vector B, and we ended up with AY BZ minus AZ BY I, then minus AX BZ minus AZ BX J plus AX BY minus AY BX K. We can write that and solve that more simply by this. So vector A cross vector B in a determinant I, J, K. We're writing in 3 rows and 3 columns. AX, AY, AZ, and BX, BY, BZ. Matrix is a technique for working with vectors and determinant. It says 3 rows, 3 columns. So if you write it this way, how do you solve this? So for element I, you take I, you ignore the column of I you're working in, and you ignore the J. So then it becomes, for I, you take these rows and columns. So for I, you have AY, it's cross multiplying basically. AY times BZ minus AZ times BY. So the column and rows of I you neglect. You don't touch AX and BX because they're in the same column of I, and you don't touch J and K. You work in here. Then for element J, first off, you always put a negative here. You have to remember, negative. Always put negative sign or minus sign in front of J. This is a always true. So for element J, that's minus J. So once again, you're now working in this column. So you ignore this and you do cross multiplication on the other two columns and ignore this row. So that'll be AX BZ. You always go this way first, then subtract this way. Go this way, and then subtract the opposite way. So it'll be AX times BZ minus AZ times BX. Lastly, for element K, we're now working in this column. So we ignore this row and we ignore this column. Then once again, it's this minus this way. That doesn't change. This way first, then you minus this way of multiplication. So for K, that would be AX BY minus AY BX. And as you see, this is exactly what we did the long way. We have AY BZ minus AZ BY, as here. You have AX BZ minus AZ BX, as here. You have AX BY minus AY BX, that's here. So determinants is a quick way of doing the cross product of vectors. So continuing our analysis of moments, the moment of a force about point O can be expressed using the vector cross product. And we will show how this is equivalent to our earlier analysis. So let's define R, as we said previously, is a position vector. And in this case, it's directed from point O, which is the point the force is causing a rotation about, to any point on the line of action of the force F. So R, once again, is a position vector. The tail is at point O, which is the point of which the body is causing a rotation about. I should say the force is causing a rotation about that point O. And the head touches any point on the line of action of F. That's R. And we're saying the vector moment about point O is equal to that position vector R cross F. That's how we're saying that. Well, then we know let's show it. This is my point O. It's my moment. Have some force F. The line of action we said extends. If I direct a position vector R to any point on that line of action of force F, it creates some angle theta here. And we said previously that the magnitude of a cross product will then be R, magnitude of the position vector, times the magnitude of force, times sine theta, the angle between their tails. Well, these angles are the same. The angle between the tail of R and F is theta. Now, the magnitude of the moment is still the magnitude of the force times that perpendicular arm, D. That does not change, remember? Well, in this case, position vector can go any point here on the line of action of the force. But that's our theta. This will be our A leg. This will be our B leg. Well, then the relationship between R and D is sine of theta. R will be the hypotenuse, and D is sine of theta. So MORF sine theta, which is the magnitude of the moment. Rearranging that, you have the moment about point O, F times R sine theta. Well, R sine theta is D. So we're back where we started from. So then how do we solve it? MO, we said, is any position vector R that extends from point O to any point on the line of action of the force F cross the force F. Well, this is vector cross vector, right? So it's cross product. So then we have to do our determinant, right? Which is our easy way of doing it, which requires Cartesian notation. So we need the X component of position vector R, the Y component, and the Z component. Then the X component of F, Y, and Z, right? So then our moment is remember, take this column, do this, take this column, do that, likewise and so forth. Always this way minus this way. So then our moment for I, the first column, we ignore the top row in the first column. So that'll be RY times FZ minus RZ times FY. Unit vector I minus, remember the second component is always negative, minus. So now we're ignoring the top row and the second column, the column with the J. We're ignoring this column now. So that'd be RXFZ, sort of like a cross multiplication, minus RZFX. J plus, now we're ignoring the top row and the last column. So it'll be RXFY minus RYFX. Okay. Let's work out an example problem that will make it a little bit clearer. Let's look on page 88. This is example in the text 3.3. So the question asks us to determine the moment produced by the force F about point O. This is in three-dimensional space. We have some point A here and some point B here. And rope. Oh, I could do better than that. All right. The magnitude of that force F is 2 kilonewtons. I'm not going to draw everything out the book so it can be a little bit neater, but we'll follow along on the book. Once again, this is example 3.3 on page 88. So we said that the moment is R cross F, all vector notation. And R being a position vector from the point O to any point that touches the line of action of F. Well, in this example, they're doing it two ways. So I can have, and this is my origin, I can have a RA that basically touches the line of action at the tree, or I can have an RB that touches it at the tractor. So back from chapter 2 on page 53 through 55 of the text, we can find our position vectors and simply by the coordinates of their points from the origin along with the unit vectors in the I, J, and K direction. Well, RA is purely from point O along the Z axis at a magnitude of 12. So RA is 12 K meters. To get from the origin O to point B, RB, you have to go in the X direction 4 meters and in the positive Y direction 12 meters. So RB would be 4I plus 12J meters. So how do we express the force in Cartesian notation, since the moment requires that both the vectors and the force be expressed in that Cartesian notation? Magnitude and direction. They gave us the magnitude. How do we get the direction? Well, we've worked previously in chapter 2. Force F is magnitude times unit vector in the same direction. This is also equivalent to magnitude of F times position vector R over R. Because the vector F has the same direction as and sense as a position vector R directed along from point A, or from point A to point B. So in this case, continue with chapter 2, we said if we have, I'm looking at page 53, equation 211, and the example figure 234A, 234A. Let's go to a clean page. So from page 53, equation 2-11, figure 234A. Z, Y, X axes. If we had a point B and a point A, it's the origin, we have some position vector R, B extending from the origin to point B, and a position vector R, A, then another position vector R that goes from the head of A, the head of A to the head of B. So this is R. Looking at this, as we said before, was the triangle rule, in that vector RA plus vector R equals to vector RP. Rearranging and solving, vector R will be vector RB, in that it's simply the difference in the coordinates of points B and point A. So it'd be my XB minus my XA I J K. So one more time, this is basically the I, J, K components of vector R, which extends from point A to point B in space. Is by taking the coordinates of each one. So the coordinates of A would be XA, YA, ZA. And this is XB, YB, and ZB, which means to get from point O to point B, I have to go so much in the X direction, so much in the Y direction, so much in the Z direction. Likewise, to get from the origin to point A, I got to go so much in the X direction, Y direction, and Z direction. So to get from point A to point B, it's the difference in those coordinates. So going back to our example problem 3.3 on 88, we left off with, I can erase this now. We calculated our projection vector RA from O to point A, and we did likewise with our RB. Well, then F from the image would be, is on the line of action from point A to point B, and that the position vector R can be drawn from point A to point B as well. So once again, from page 55 in the text, I rewrite it so we can follow it now. We should be refreshed and up to date. Force F is the magnitude of F times the unit vector, or it can be written as force, the magnitude of F times position vector R over the magnitude of R, as long as they share the same direction and sense. which in example problem 3.3 they do. So then R, as we said from our review of chapter 2 work, R is RB minus RA. And we simply subtract the coordinates. RB has I and J coordinates, or X and Y, and RA only has Z or K, right? So R is RB coordinates minus RA. So that's 4I plus 12J minus 12K, because it's minus RA. This is meters. But here is the vector R, position vector R, over the magnitude. And we know the magnitude is just the square root of each component. So it'll be 4 meters squared plus 12 meters squared minus 12 meters squared, right? So then our F is the magnitude F, which is 2 kilonewtons, times R, position vector R, over R. So that's 4I plus 12J minus 12K meters over the magnitude of R, which is the square root of 4 meters squared plus 12 meters squared plus minus 12 meters squared. Write that on a clean page. So once again, the vector F in Cartesian notation is the magnitude times the position vector R over the magnitude of the position vector. So we said that's the 2 kilonewtons times 4I plus 12J minus 12K meters over square root 4 meters squared plus 12 meters squared plus negative 12 meters squared. F is equal to 0.459 I plus 1.376 J minus 1.376 K kilonewtons. So that's the force in Cartesian notation. But the question is asking for the moment. Moment about point O is R cross F. Well, remember R is any position, is a position vector that touches any point on F. So this example in the book is doing it two ways. We can do it using the RA or the RB. So using RA cross F, using our determinant setup, I, J, K, RA was just 12K. So it's 0I, right? 0J, 12K. F is 0.459I, 1.376J, and negative 1.376K. This is equal to, with the I, you ignore the first column and top row. So that's 0 times minus 1.376 minus 12 times 1.376 I. For the J, we start with our negative. You always put the negative sign first. So you ignore the second column in the top row. So that's 0 times minus 1.376 minus 12 times 0.459 J. K, you ignore the top row in the third column. So that's 0 times 1.376 minus 0 times 0.459 K. This equates to the moment. Multiplying that out, you get 16.5 I plus 5.51 J. This is kilonewtons meters. And if I did it using position vector B, RB cross F, once again set up my determinant, I, J, K. For position vector RB, we had an I and J component, but no K component. So that was 4, 12, 0. No K component. F, once again, is the 0.459, 1.376, and a negative 1.376. Moment about 0.0 is, once again, for the I, you ignore the top row in the first column. So that's 12 times negative 1.376 minus 0 times 1.376 I. Subtract the second term for the J. Remember, it's always negative. You ignore the second column in the first row. So that's 4 times negative 1.376 minus 0 times 0.459. This is J. K, you ignore the top row in the third column. So this is 4 times 1.376 minus 12 times 0.459 K. And this gives you the same answer, which proves what we've been saying, that is any position vector that touches any point on the line of action of the force. Let's do another example problem. Example 3.4 in the text, page 89. So here, once again, we're in three-dimensional space. They want us to determine the resultant moment the forces create at about the flange at point O. There are two forces. You have so you got your F1 here. They gave it to you in vector format, Cartesian notation, 60I plus 40J plus 20K pound force. So F1 is point A. And you have a F2, 80I plus 40J minus 30K pound force. All right. That's our point B. So we'll start off by remember our moment is position vector cross F. We want to know our moment, so let's create some position vectors. From the origin, O, which is what we're rotating about, to the lines of action of the two individual forces, F1 and F2. Well, simple enough, we have a RA straight across from the origin, so we'll call this RA, from the origin to the line of action of F1. RB, from the origin, will come straight down this way, following the text. Remember, it can touch any point on the line of action of the force, and it will be the same. It just makes it easier this way in the text because the coordinates have been laid out for us. So for RA, that is straight on the y-axis at a distance of 5 feet. So it's just unit vector J, so 5J feet. For RB, to get from the origin to point B, you have to come in the positive x direction, a value of 4. In the positive y direction, a value of 5. And then in the negative z direction, because you're going below the axis, a value of 2. So let's rewrite that here. We said RA is purely on the J or Y axis. B so then our resultant moment of both forces cause about point O is the sum of each moment. So it's be R cross F for each force that is caused. So that would be RA cross F1 plus RB cross F2. Setting up our two determinants. So the RA is just a J. It has no I or K values. So 0, 5, 0. F1 has values for I, J, and K. Minus 60, 40J, and 20K. For my RB, we have I, J, and K values. So that's 4, 5, negative 2. And my F2 is 80, 40, negative 30. So the moments, you have to do it the same way. Let's do it on a clean page. So once again, for the first determinant, for the I, we're ignoring the top row in the first column. So it's 5 times 20 minus 0 times 40. I. J is always, the J term is always negative. So the J, we ignore the top row in the second column. So that's 0 times 20 minus 0 times negative 60. J. Plus, for the K, we're ignoring the top row and the third column. So 0 times 40 minus 5 times minus 60. Okay. Now for the second determinant, we have, ignoring the top row in the first column for I, we have 5 times minus 30 minus negative 2 times 40. I. Once again, minus the J term, and we're ignoring the top row in the second column. So that's 4 times minus 30 minus negative 2 times 80. J. For K, we're ignoring the top row in the third column. So that's 4 times 40 minus 5 times 80. K. Doing the math, simplifying it out, you get the moment, the resultant moment that's caused by forces F1 and F2 about point O is 30I minus 40J plus 60K pound force feet. And we'll stop here for today. If there are any questions, please send me an email. Have a good day and work hard.